Sliding window maximum. You are given an array of integer nums. There is a sliding window of size k which is moving from very left of the array to the very right. You can only see k numbers in the window. Each time the sliding window moves right by one position. So we have to return the maximum sliding window. So max of each sliding window. That's what they mean here. So if we have, this is the sliding window, this is the nums we have, and k is 3, means we are having 3 length window. So this is the first window. The max of this window is 3. Next window is 3 minus 1 minus 3. The max of this window is again 3. This is the next window. The max here has changed to 5. So this is the max. So this way we'll be calculating the max of all these windows. Now how do we solve it? So the brute force way is we'll just move one element at a time, and for each window we'll calculate the maximum going through all the elements of this window. But that's not a optimized way. We need to find a better way for this. So consider this is the array 1 3 minus 1 minus 3 5 3 6 7, and k is 3. So this is the first window, this is the second window, this is third window, and so on. So what is the max for the first window? This is the max. For the second window, still 3 is the max. For the third window, minus 1, minus 3, 5, max is 5. So how do we calculate this? So when we are shifting our window from the left to right, we are just adding one element in the right side. So we added, when this is the first window, when we moved here we added minus 3 and we got rid of 1. So if this window, this is ending at I equals to 0, 1, 2, 3, and our I is 3 and k is also 3. So I minus k is 0. Till 0th index I have to remove the elements. Then we will get a new element. So how do we calculate this maximum elements? The brute force approach will be, for each of the window we'll just go through the elements, go through the numbers, and we'll get the maximum. But is there any better way? Can we use some extra space to find out the maximum for each window? So each time, consider a data structure. We're not sure what kind of data structures we need. It's a stack, queue, heap, or we don't know. Just consider one data structure we're taking, and we'll process one number at a time. So first we are having 1. Then we are having 3. So we are not, the k is 3, so we have not processed all elements for the first window. So when we got 3, will 1 become the max anytime? Doesn't matter what is the value of k. Just that we got a 3, 1 can never become maximum for this window. So we can get rid of this one. Next we are adding minus 1. Minus 1 is less than 3, the current max, so we can keep it. So this is the first window we got, and the maximum is this one. Next we are adding minus 3. What is the index of minus 3? That is 3, and we have to get rid of elements from till 0th index. So but we have already removed the 0th index element, that is 1. So this is my current window. What is the maximum element in this window? This is still 3. Next we are adding 5. So we got an element, so we got a number that is greater than the current max. And also when we added 5, the index of 5 is 4. We have to get rid of elements numbers till 4 minus 3 1. Still first index we have to remove the elements, so we have to get rid of 3. Now this is my window. What is the maximum here? 5 is the maximum. Now consider one thing here. Next we will be moving our windows in the right side, right? So but still in our data structure whatever we have -1 and -3. So when we'll move our window in the right side, we'll first get rid of -1, then in the next step -3 and then 5. So as long as we have 5 in our data structure, will -1 or -3 ever become maximum for any window? It cannot be, because we are getting rid of those elements first, and 5 we already have. So 5 will become, as long as we are not getting any better, any maximum, any element, any number that is larger than 5. So we don't need this -1 and -3. We can just get rid of these elements. What we can do is, whenever we are putting any element in this data structure, we can just remove elements that are less than this current element. Like when we are putting 5, we can get rid of -3 and -1 from this data structure. Next we are getting 3. What is the index of 3? Index of 3 is 4, 5. Index of 3 is 5. So we need to get rid of elements till 5 minus 3, that is 2. So 0, this is 0, 1, 2. Till 1 I have to get rid of. So my window will be this, right? So what is the maximum in this window? But we have already removed index till index 2, so we don't have to remove anything here. But what is maximum here? Maximum is still 5, because we haven't got any better element. So 5 is still the maximum. Next we got 6. When you got 6, 6 is at index 6, right? So 6 minus 3 till 3, index 3 I have to get rid of. So we have to get rid of till -3. -3 we already have removed from our data structure. So currently we have 5, 3, 6. Sorry, we have 5, 3, and now we are putting 6. So before putting 6, we can get rid of 5 and 3, because as long as we have 6, 5 and 3 can never become maximum. Next this is the maximum now. Next we'll be putting 7. When you're putting 7, what is the maximum? Before putting 7, we can just get rid of elements that are lesser than 7, right? So well, in the max at this moment will be 7. So what we are doing is, we have a data structures. So at any point, for any index, when we are adding that element, and then we are removing element from it where I minus k equals to 0, less than equals to 0. And then we are we are doing from the left side, and from the right side what we're doing is, when before putting that element into the data structure, we are deleting all the elements that are lesser than the current element, because we don't need that. If we are having a better element, then we don't need any lesser elements. So those elements we are removing from the tail, right? So we are saying we need a double-ended queue or DQ kind of data structure. Now let's look at the code. So we need a DQ. Consider this is, we are calling it Q, and here we'll be storing the number and the index of each element, each number. So I will be going through each number. Let's first take one output variable, output list, where I'll be adding my outputs. So for each index, we are just doing two things. We are getting rid of elements from the left side first. So let's do that. While q is not empty, and q dot 0 dot 1. So 0 is the first element and 1 means it's the index of that element. That index is less than equals to I minus k. Then we are removing from the left. Next, what we are doing is, before putting that element in the data structures, we are just removing elements from that are lesser than the current element, and that we are removing from the tail of the queue. So while q and q minus 1 0, so minus 1 is the last element and 0 is the value of that element, is less than current element, that is nums of I. I am removing from the tail. So this is pop left and this is pop. This is from the left side, this is from the right side. After that, we'll put the current element. What we'll put? We'll put the value nums of I, and this is the index. Now we have to add what is the current max at this index. That will be whatever the element at the front of the queue, that will be the current max for this index. But then again, one thing here, so for the first max we are calculating for, if k is 3, we are calculating at second index. For the 0 and 1 index, we are not calculating anything. So the window calculation, the window max calculation will start from k minus 1 position. So if I less than k minus 1, we can just continue. Otherwise, what we'll do is we'll add the number to the output. So that is q 0 0, leftmost element of the queue, the value of the leftmost element of the queue, and that's it. We can just return the output. Something. Wow. Let's run this. It's pretty efficient. So what is the time complexity of this algorithm? So it is order of n, because we are just going through the nums only once, and this is order of n, and we are taking extra memory, that is also order of n. Let's just verify that. So this is order of n.